Hi guys, so in this episode we're going to talk about I/O and, well, just getting information inside your programs. So we have been using this I/O monad for a while. Well, not a lot of it, but this basically, the I/O type is a type that works as an interface between your programs and, we could say, the outside world. You use the I/O type for sending data out, for instance, for sending data to the console, to the terminal, to standard output, or reading something, or maybe reading from a file, or communicating over the network, that kind of stuff. So that is what the I/O monad is for, communication. Now, we're not really going to explore too much about how to use the I/O monad, because the I/O library in Lux, the LuxNet library isn't so rich. There's not a lot of stuff right now. Right now, most of what you use for I/O is stuff that is wait, forget. Anyway, when you want to do I/O, most of what you do is just interact with the host platform. In this case, the JVM, because that's where you will find all those streams, the Java.io package, all that stuff. That's what you will tend to use for I/O, and you will use the I/O type to lift that into a more easy to handle way for Lux. So even though we're not gonna see too much about actually doing I/O in this episode, we'll see hopefully more of that in the next few episodes, starting from the next episode, because starting with the next episode we're gonna talk about doing JVM intro. However, I will talk about what is the structure of the I/O type and how does it work. Now, the most programming languages, even most functional programming languages, don't have such a thing as an I/O type. I/O is something that implicitly happens sometimes in a program, in some functions. For instance, a function could be printing something to standard output and you might not know it unless you read the documentation. A function could depend on mutating some data somewhere and you might not know it unless you read the documentation. So I/O and mutation and other kinds of imperative side effects in most programming languages happen in a completely implicit way. So there is one language though that is very well known for separating I/O from the rest of the language, and that is Haskell. Haskell has a special I/O type that serves pretty much the same purpose as the I/O type in Lux. In fact, Lux got the I/O type as an inspiration from Haskell. However, there is a difference between how both types are implemented. In the case of Haskell, the I/O type is kind of a wrapper for some kind of special magical way the compiler works. The compiler tries to wrap this real world information using the I/O type. But in the case of Lux, the I/O type is a little bit more straightforward, even if somewhat weird. The I/O type is actually defined this way. I know this looks weird, but let's take it by steps. So an I/O type is just a function, right? And that is important because I/O operations need to be evaluated before they yield a result, because we are turning I/O into a thing instead of just something that sometimes happens in a more informal way. So the way we reify I/O into the language is by turning it into a function. And the only way for you to get the side effect of the I/O operation is by invoking the function and then getting the result. Simple as that. So that's the way I do, I/O as a separate thing from the language, by turning it first into a function. Now, this function here takes an argument that is very weird. It is called void. So what is void? So you might remember that we have seen, several different kinds of types, and one of them was unit. And the unit type corresponds to the empty tuple. So a tuple of two elements will have a type that is, prod t, in this case, text real. While an empty tuple will have a type that is just unit t. And tuples of one element is just the same type as the original element, and tuples of more than two elements just nested products. Well, we also have something similar for variants. A variant of left one or right 2.0 will have something like some t text real so we have this version of its kind of type that is kind of a mirror or a reflection in some way of prod t, of the product types. Some types have the same structure as product types, but is there something similar for unit? Well, it turns out there is, and it's called void. Now the thing with void is that void is a little bit different from unit in one particular aspect, and that is, whereas unit is called unit because there's only one possible way to make it, which is just the empty tuple. There's only one way to make an empty tuple. You might be able to intuit why void is named void, because it is impossible to make an instance. That it is a very weird type because it has that property. You cannot make an instance of void. It is impossible. And if you really think about it, you just consider this. In some types, even if some type contains two members, you can only have one of these two members. So some types allow you to alternate between multiple possibilities, but at any given point you can only have one possibility, one option. Void is kind of like saying, hey, I have a variant of no options. In the same way that unit is like saying, hey, I have a tuple of no elements. Problem is, whereas a tuple of two elements is just some empty data structure, an empty variant is like saying, hey, I have an option without any content, without any possibility. It cannot possibly be, so you cannot make an instance of this. And because of that, you have this weird type that can have no member. You can never make an instance of void. It's impossible. Now this might look weird because we're saying here that an IO actually takes an instance of void. So how can that happen? And the reality, well, I'm not going to explain how it works. I leave that as a secret sauce, but it's not really very mysterious if you become more comfortable with loops and understand how it works. But the point is, I can kind of come up with my own instance of void with some simple trickery, and that's what I do. The idea is to use this type, which is fairly inaccessible, and most people are never going to use it. I mean, the only way for you to ever make an instance of void is if you really want to make it. I mean, you're going to make it by accident, you're going to make it by just writing normal code, because void, instances of void don't show up anywhere. So for that reason, I decided to do things that way. So in order to get the side effect of a IO type, all you need to do is invoke it with a void, and you're gonna get the side effect. Simple as that. And this IO monad, as we saw in the episode on monads, and also the previous episode on seeing syntax parsers and monads under the hood, we know that when you use denotation and monadic structures, all the computations we make are within that monad. So the IO monad composes several side-effecting I/O computations and fuses it all into one computation. And eventually, the program, the main method generated during program compilation just runs that, and your program runs just like that. So again, when we talk more about Java interop, and even about concurrency. We're gonna see more of I/O. We're gonna see some practical applications of stuff like this. And finally, the last thing that I wanted to talk to you guys about was command line interfaces in Lux. You see, there is a module in the standard library called CLI. And what CLI does is that it contains a variety of functions. And even contains the definition of program. In order for you to make a program, you need to import the CLI module, which is why we're importing it here. And the reason is that in programs you can take CLI arguments, and we can already see here kind of how it works. As you can see here in these examples, really good examples actually. If you just give it here in our program definition, if you just give it the name of a variable, then all the arguments are going to be put in there. So we're just going to receive all of the arguments to our function, to our program, sorry. We're going to receive all of the arguments as a list inside a variable. If instead you give it a list of elements in parentheses, you're going to get something very similar. Actually, pretty much the same way. It works pretty much the same way as def syntax, except that instead of us parsing syntax tokens, AST tokens, we're going to be parsing command line arguments, which are just text, piece of text, piece of strings. And this works pretty much the same. You have these parentheses. Here we're only taking one argument, so basically this means, hey, this program only ever gets one argument. We're going to bind it to name, and this name is a piece of text, so we can use it wherever we want. Or you can do more complex parsing with the same syntax you use for syntax parsing. A tuple, the first element is the name of a variable, and the second element is the name of a parser. You cannot use the parser from syntax because we're dealing with text, but the CLI library already comes with several parsers. Many of them mirrors of the syntax parsers. They look the same, they work pretty much the same, and you can just use that. Simple as that. You can have all the complex parsing you want for your command line arguments, and even the type for CLI looks pretty much the same as for syntax parsing. Only that instead of working with lists of AST, we're working with lists of text. So check this out. If you give me a list of text, I'm gonna give you back an error of an updated list of text and an A. It looks the same as for syntax parsing, just the same. So you can imagine that the code is gonna be very, very, very similar. So yeah, that's it. So finally, let's see that in action, and maybe try to get something out of this, something simple. So let's see. Let's make here a small program that uses these parsers. So we're gonna be receiving the name of the user, I don't know, and then we're gonna be receiving the list of words. So this nil, we're just going to say screw this. Let's not have any prefix here. Just have them online. So here we have this. If nobody gives me any, I don't get any words, I just say this. Else there we have it. So let's compile this. It appears we got an error. Oh, I know what happened. We didn't replace args with words. Indeed, definition does not exist. There we go. So if we invoke this program, now something interesting is going to happen. I'm going to invoke it with no arguments. Let's see what happens. Bam! Can't extract from empty arguments. That's actually an error that comes from using this this little parser for arguments. You see, this in the same way that for syntax, for def syntax, if you don't give anything a parser, you get ID as a automatic syntax parser. Here, if you don't give a name, you get R, which is basically just like ID, but for CLI arguments. And you know, if the list of arguments is empty, you get, hey, can't extract from empty arguments. So we need to invoke this with at least one argument in the first position also. So I invoke this here, and we get hello Eduardo, really nice. And if we invoke this program with more arguments, 1, 2, 3, 4, 5, bam, it works just as expected. So we actually have a nice library for working with command line arguments right in the standard library. Simple, fast, powerful. Really nice. So in the next video we're going to be talking about host interrupt, and we're finally going to be seeing how to work with JVM code. It's going to be pretty exciting. See you then.